A very good afternoon, everyone. We'll start our today discussion. It's 3 p.m. right already. We are right now in the third week. Sorry, we are right now in the sixth week of the Introduction to Material Science and Engineering course. Today I'm not doing that printout and uh, so most of the things are handwritten today. I came to my home and because of that, I not had few facilities available over here. But I will more or less I will try to keep things as it was before. Let's go to the list of the content that has been covered in this particular week. In a class, we have saw that we discuss about the geometrical properties of the dislocations, geometrical properties of the crystal, geometrical properties of dislocation. We can see that surface and the grain boundary, dislocation node, and dislocation loops. These are the things that has been discussed. Along with those, we discuss about the dislocation motion, like climb, slip, and glide. We studied that how the different dislocations, for example, screw dislocation, edge dislocation, and the mesh dislocation will behave, which can glide, which can climb, and which can slip. Cross slip. So those things we have discussed. Then we went to the two-dimensional defects such as the surface defect and interfaces. We also discussed about that how the stacking fault, what is the stacking fault, and how it can be generated in the crystal. Then we discussed about the twin boundary, like the boundary about which the entire stacking sequence is seen to be the reflected, like a mirror. And we have also studied that the twin boundaries are mostly occur in the pair in the crystal. They don't occur in a single. Like the one boundary doesn't happen that okay, one boundary is coming. So both two boundaries will come together, and in between them, the the nature of the lattice will change. The sequence of the lattice will change. Then we discuss in detail about the grain boundary, what it is like in the previous class also, lot of things. We were using this term the grain boundary, but in full-fledged way, in this particular week only, we discussed about what is the grain boundaries, how, what are the different types of grain boundary, what is like the, we can say tilt grain boundary and twist grain boundary, those things we have discussed. We discussed about the low angle grain boundary, we discussed about the high angle grain boundary. So we typically say that if something is less than 5 degree, we will consider it to be the low angle grain boundary. And while if it is more than the 5 degree, we will consider it to be the high angle grain boundary. Again, in the various literature, in the various research paper, you will find that this variations is not that like it's not very sacrosanct. Like one people sometimes also use 10 or 15 degree to be the less than 15 degree to be the lower grain boundary. It again depend upon the perspective of the researcher and the severity of the work that has been done. But for our course, we'll keep in mind that below 5 degree we'll consider it to be the low angle grain boundary, and above 5 we'll consider it to be the high angle grain boundary. So these are the list of the content that has been covered in the class. Now, if you guys have any doubt in this particular entire thing, in this particular entire section that has been discussed in the week 6, you can please feel to text me. You can feel free to reply in that comment box, and you can also comment onto the video which is going to be uploaded in the YouTube. So, if there is no doubt, we'll proceed to our doubt solving question session, where we are going to discuss about the list of the questions. Let's start with the question number one. Okay, so let's read it. So the question is telling that which of the following is not a possible way of dislocation line to terminate? Which of the following is not a possible way of the dislocation line to terminate? So let's see that where and all dislocation can terminate. Can it terminate on the surface? We know that, yeah, a dislocation can terminate on the surface. Always remember, dislocation, it's a defect. If it want to terminate, it will terminate on the defect itself. This defect can be surface, it can be grain boundary, it can be stacking fault, it can be twin boundary, or it can be the dislocation itself, because this itself is a defect. So itself also. So we can consider, okay, I can terminate on the free surface, that's right. It can terminate on the green boundary, that's right. It can terminate on the another dislocation, that's right. These are the right things inside the crystal without any connections. So this one is telling that it can end abruptly. This last point. So this is incorrect, right? So this is incorrect. And our question was asking which is not a possible way. So our right answer will be the option D is the right answer. So this location cannot terminate like this. It cannot end abruptly inside the crystal. These are the points which we need to remember always. Okay, so with that we have solved the question number one. If there is any doubt regarding this question, you can let me know. You can put on the comment box. I will definitely reply to it. Let's move to the next question, question number two. Uh, what is one of the key geometrical properties of a dislocation line? So what are the properties of the dislocation line? A dislocation line can end abruptly inside the crystal. We know that it is not the case. It cannot end abruptly inside the crystal. So this is not the geometrical properties of the dislocation line. A dislocation cannot end abruptly inside the crystal. This is right. Just now we have discussed in the previous question itself. Now, a dislocation always forms a straight line. No, it's not the case. A dislocation, it shouldn't be like this. It can be like this also. It can be like this also. Various TM, transmission electron microscopy structure, like images, has confirmed that the dislocation line can form the wavy structure, like it can be in the wavy way. It shouldn't be like it should be the straight line. So this is again incorrect. A dislocation only exists in the perfect crystal. See, if the crystal is perfect, why would the dislocation will be present? So this is the highly incorrect. Like I shouldn't have put this option also in the question. So with that, we have solved the question number two. If there is any doubt, please let me know. Let's move to the next question, question number three. Here we can see, like, if a dislocation end on another dislocation, what it form? Now they're asking, okay, what we are doing is that, okay, we had one dislocation. Now this dislocation is ending on the another dislocation. So now what is this? Is it a grain boundary? Is it a stacking fault? Is it a dislocation node or a void? We know it's not a void. For void, we know we need a more number of vacancy clustered together. Something like this. More number of vacancies will be clustered together, then only we can say that it's a, pardon me, it's a void. So it's not the case. We know one dislocation is intersecting the another dislocation. Both are the 1D defect. So their intersection will have the zero dimensions. So a grain boundary cannot be formed. A stacking fault cannot be formed because it's a planar defect. The dislocation node is the one, the point which is created is a dislocation node. We'll call it to be the dislocation node. So if I have one dislocation is ending on the another dislocation, the point that has been created, it is not that the dislocation node. That is our question number three. Okay. Okay, let's move to the next question. Uh, you will find a similar type of question in the assignments. So now, yeah, now we have to do match the following type. Column A and column B are there. Let's match the edge distribution among this. Among which one will this edge distribution will match? A dislocation that move perpendicular to the applied stress. Uh, we know in the edge dislocation it's not the case. In edge dislocation, a dislocation will move parallel to the applied stress. A screw dislocate. Next, a boundary between the slip and unslip region. That is right. Okay, edge dislocation. We can say that it's a boundary between the slip and unslip region. Now the screw dislocation, a dislocation that move perpendicular to the applied stress, that is right for the screw dislocation. What about the dislocation node? A dislocation node, we just discussed about it. A form when the dislocation intersect with each other. Now only the remaining part is 4 and C, but still let's see. Dislocation loop. A closed dislocation line that has the no starting or the end. So this is a dislocation loop. We can say that a dislocation has ended on itself and is forming the loop. So it has no starting or end point. So one is B, A, then B, A, D, and C. So this is our final answer. If there is no doubt, we'll move ahead. We'll go to the next question, question number 5. A single crystal is characterized by, so now they are talking about the single crystal. We know that if it is single crystal, it won't have any grain boundary. So we know that no grain boundary. So let us say that this is our single crystal. It has random oriented unit cell. Is it the case? No. In a single crystal, it consists of the only one grain, and we know it's a crystal. Crystal will have a uniformity of the in the unit cells. They all will follow the translation symmetry. Multiple crystal oriented within a same sample. They are telling that we are having the multiple crystals. Like let's say this is the one, and we can divide it like this. So in one of them, the crystal orientation is like this. In another case, crystal orientation is like this. Here it's like this. We know this will happen in the polycrystal, not in the single crystal. So again, this is also incorrect. Now let's move to the third one. Identical unit cell oriented throughout the stem. That is right. It will have one single orientation throughout the sample. The presence of grain boundary, we just said that if it is single crystal, it won't have any grain boundary. And so with that, we saw our first 5 question is over. Any doubt in this first 5 question, then you can always uh, comment on the comment section. 2 and 1. These are the 5 questions that has been over now. Let's go to the next question, question number 6. Oh. A polycrystal sample consists of. So now we just discussed about the single crystal. Now we need to discuss about the polycrystal. We have saw that this is the polycrystal separated by the green boundaries. So it will have a multiple grain with identical orientation. It will have multiple grain, that is right, but with identical orientation. See, if their orientation are identical, if their orientation are same, then there is no grain boundary itself. There will be one. They will contribute towards the one single crystal. There won't be the two different crystals. So again, it's incorrect. A single grain with a uniform periodicity. We know that a single grain. No, it's not a single grain. We're talking about the polycrystal. Poly means many. Multiple grain with different orientation. Now, multiple grain, no, we know that it will be there, and the different orientation. They all will have the orientation different. That's right. So option C is the right answer. Here also we have saw that we are having the multiple grains. For example, grain number 1, 2, and 3. We have the different multiple grain, and their orientation are also different. Like it is having the somewhere this type of it's vertical orientation. It's again tilted to the different direction. So they have the different orientation. Now, if we see the last one, a perfect crystal lattice without grain boundary, no, it is not the case. If this is the case, then it will be the single crystal. So now, more or less, in much more detail and much more like it's stuck now in our mind that what is single crystal and what is polycrystal. The single crystal is the one having the one single orientation throughout the crystal, throughout the sample, while polycrystal will have multiple grains, and the orientation of the grain will also be differ from each other, from the neighboring grains. Let's move to the next question, question number 7. Let me hide the question number 8. We'll focus only on one question at a time. Why can't line cross the grain boundary? So now, let us say this is a grain boundary. Here the crystals are having this particular orientation, while here the crystal is having this particular orientation. Now one edge, if if it want to cross, edge dislocation, like a dislocation line want to cross, let us say any dislocation we can consider, we are considering this dislocation. If it want to cross, so it will travel across the lattice like this. Let's say this is our strip plane. It will travel along this. But now here he can the dislocation will feel that the obstacles are there. The periodicity which a crystal was having before the grain boundary, the symmetry which was having, the orientation which was having before the grain boundary, before this grain boundary was is different now over here. So now here it will stop because it don't know that if it follow the same direction, he is not finding any other slip direction for a slip plane over here. Here the slip plane has distressed. Let's say this is the slip plane and the slip plane has changed its direction. So now this is the question that why dislocation cannot cross the grain boundary. The orientation of the lattice plane changes across the grain boundary. That is right, and we know that this is the case over here. If the lattice orientation will change, the slip plane will also will change the orientation of it, and so dislocation will not find the same oriented slip plane as it was like before. Dislocation only exists in the single crystal, absolutely incorrect. Dislocation exists in the single crystal as well as the polycrystal. Grain boundary repel dislocation. Is it the case? No. Even if it is the case, let's say grain boundary is repelling the dislocation, still like multiple dislocation pile up can occur and they can break it. So this is not the primary reason. We'll say that it's incorrect. The grain boundary dissolve the dislocation. Now they are telling that the grain boundary is going to consume the dislocation, and that is the reason why that the dislocation is not able to close. And we know this is not the case. The main reason why it is not able to cross is due to the orientation difference across the grain boundary. So with that, we have solved the question number 7. Let's move to the next question, question number 8. So here, a Burgess factor of the dislocation depend upon. So now they're talking about the Burgess factor. On what factor does it depend upon? A type of dislocation, orientation of the grain boundary, uh, chosen convention of the tangent vector direction, that is, it will depend upon the t cap if they are telling, and none of the above. Let's see top 3. See, we know that Burgess vector, the concept is associated with the crystal lattice. FCC will have its own, BCC will have its own Burgess vector. Now it will depend upon the nature of the dislocation, whether it's an edge or it's a screw. Okay, so it will depend upon the type of the dislocation. It won't depend upon the orientation of the grain. No, it won't depend on the orientation of the grain. The Burgess vector over here in the grain 1 and the Burgess vector in the grain 2 will be exactly same. They won't differ from each other. So the grain boundary, the orientation of the grain boundary is not the one which is going to decide that what is the Burgess vector. The chosen conversion of the tangent vector direction, no. A tangent vector direction will always be along the dislocation line. So while there is no relation between the B and T, Burgess vector and the tangent vector. This is incorrect. The only answer right to the correct answer is the type of dislocation it will depend upon. It will also depend upon the crystal structure. So I can write the one more thing over here. that instead of none of the above, I could have write that okay, that will depend on the crystal structure of the material. So that would also be the correct option. Okay. Okay, with that, we have solved the 8 questions. Let's move to the next question, question number 9. Now it's the master pair. A dislocation node. So here are the list of the concept, and here the corresponding definition is listed in the column B. We have to find what is the dislocation node. Uh, sum of the Burgess vector at the node equal to 0. Is it the talking about a dislocation node? No. A point where the multiple dislocation meet. This is the right one, right? If we are having dislocation 1, let us say, dislocation 2, dislocation 3, this point is the one which is called as a node. So we can say that a point where multiple dislocations are going to meet is known as the node, dislocation node. Frank rule. Frank rule, we know that Frank rule says that the sum of the Burgess vector at the node will be equal to 0. So we'll match 2 with option A, sum of the Burgess vector at the node equal to 0. Now what is the Burgess vector? Represent the amount of the slip due to the dislocation. All vectors should be taken in and out at crystallographic plane where the slip occur. We know a Burgess vector represents the amount of slip due to a dislocation. It will match with this. Slip plane. Slip plane is the one which tell about that the where the slip occur, the crystallographic plane where the slip occur. This is the slip plane. So 4 will match with the E. And the tangent vector, we know that tangent vector convention tells that either all the, if we are talking about a particular node, whether all the tangent should be pointing towards the node or they should be pointing, all should be pointing away from the nodes. This is the tangent vector convention. It shouldn't happen like, okay, one is pointing toward the node, one is pointing away from the node. That is not the convention says. Convention says that all the tangent vectors should be taken in or out of the node. You should follow only one. Either it should take in or you should take out. That's all. And so with that, we can say that our correct answer is B, A, C, E, and D. Okay. Now let's move to the next question, question number 10. Just a minute. Yeah. So the question number 10. A dislocation loop is a dislocation line that form a straight line, terminate on itself. It's always a screw dislocation, can exist in the polycrystal, can only exist in the polycrystal. See, this only what is the problem. So I will discard it because it can also exist in the single crystal. Now the dislocation loop they are talking about, what we know that in a dislocation loop, a dislocation is starting from a point and it is ending on itself. So the starting point and ending point is the same. So it forms a straight line. We cannot say that. It's forming the loop. Loop is not a straight line. Terminate on itself, that's the right answer. Let's say it's starting from here and it's ending here. The finish and the starting point are same. It's always a screw dislocation. No, it's not the case. We have seen the prismatic loop also in the class. So now let's talk about the prismatic loop. A prismatic dislocation loop is characterized by varying Burgess vector, the Burgess vector being perpendicular to the loop. The dislocation change its characteristic continuously, having only the screw dislocation. We have seen that if this is my loop, in the prismatic loop, what will happen that so the tangent vector is first of all is along the loop, while the Burgess vector will be always perpendicular to the loop. So our right answer would be the Burgess vector being perpendicular to the loop plane. So this is a loop plane, let us say, in which the loop is lying, the dislocation loop is lying. And now it is, now that this is how we have formed the prismatic loop. Okay. So with that, we can say that the option B is the right answer over here. Let's go to the next question, question number 12. Again, the match the pair type. You can see that nowadays, even in the gate, lot of multiple choice questions are coming. Sorry, match the following questions are coming. More or less like 7 to 8 questions are mostly match the pair. So that's why we are also focusing more onto these things. Now let's go ahead. The edge dislocation. Here again, the terms are written over here, and there the description is written over here. So let's talk about the edge dislocation. The Burgess vector parallel to the tangent vector. So here they are telling that the Burgess vector is parallel to the tangent vector. That is the dislocation line. Second case, Burgess vector is perpendicular to the tangent vector. The Burgess vector is perpendicular to the dislocation line. We know in the edge dislocation, this is the case where the Burgess vector and the tangent vector are perpendicular with each other. While in the screw dislocation, they are parallel to each other. Regarding the mixed dislocation, combination of the edge and the screw component. So it will the mixed dislocation will have both edge and the screw component. So it will match with the option 4. Prismatic dislocation loop, we just now discussed that. In the prismatic dislocation loop, Burgess vector will always be perpendicular to the loop. So Burgess vector perpendicular to the loop plane. So P will match with the 5. And vacancy loop form when the vacancy condense in the closed pack structure. So we can say that the E will match with the 3. If we take a plane and we put in that plane, we are condensing a lot of the vacancy. They are coming together. Then we can say that they are forming the vacancy loop. And that's why we can say that the option E will match with the 3. So the correct answer is 2, 1, 4, 5, and 3. Okay, let's move ahead. Now, what type of dislocation can undergo the cross-slip motion? Cross-slip we are talking about. And in the class, we have studied that dislocations can climb, can glide, and can what we can say cross-slip. A glide motion is shown by both screw dislocation and edge dislocation. Climb, if we talk about, it is only shown by the edge. While if we talk about the cross-slip, it is shown only by the screw. So the what type of dislocation can undergo the cross-slip? So we will write, we'll go for the cross-slip we are talking about. So it should be the screw dislocation. Right. We are not going to write the mixed dislocation because it is also having the component of the edge in itself. And that is something which is not going to the cross. Let's move to the next question. In a glide motion, the motion of the edge dislocation occurs. In a glide motion, the motion of the edge dislocation. Now we are talking about the edge dislocation. Point to be noted. So now, in an edge dislocation, perpendicular to the Burgess vector, parallel to the Burgess vector, randomly in any direction. In a edge dislocation, we know that along the Burgess vector, a glide will occur. Right. So it will be the parallel to the Burgess vector. Option B is the right answer. See, in this type of questions, people usually get confused. So I wrote down the few concept over here. So the concept says that for the edge dislocation, the stress component is along the Burgess vector. The dislocation motion is also along the Burgess vector. So both the things are happening over here. The stress Thus, critical result shear stress is along the Burgess vector itself, and the dislocational motion which is happening, that is also along the Burgess vector. Now, if we talk about the screw, the stress is along the Burgess vector. These three things, the dislocation line, the Burgess vector, and the critical result shear stress, they all are parallel to each other, while the motion of the dislocation is perpendicular to all three of them. This is the thing which we need to remember, right? So the dislocation line and the Burgess vector and the stress, the critical result shear stress, they all are parallel to each other, and they all are perpendicular to the dislocation motion. Okay, with that, if we keep this thing in our mind, we'll be able to solve all the questions in regard to this. And so we can say that if we are having critical result shear stress and the Burgess vector and the dislocation line, we'll say for the screw dislocation, they all will be the parallel with each other and they will be perpendicular to the dislocation line. Okay, so now let's move to the next question, question number 14. Sorry, question number 15. The motion of the screw dislocation under the shear stress is, so right now, just now we have discussed about it. The motion of the screw dislocation we are talking about under the shear stress. What we have studied, if we talk about the motion and the shear stress, it is a perpendicular to the shear stress, right? So the dislocation motion in the screw is always perpendicular to the dislocation line, Burgess vector, and the shear stress. So perpendicular to the applied stress. We can say that the option B is the right answer. What happened when an edge dislocation swept through the entire slip plane? So this is something which has been discussed in the detail in class. So we are having a dislocation. Now what will happen that if this dislocation swept, it started traveling from here to all the way to the surface. What will happen? What is going to happen in that case? This the line number 1 is over here, the line number 2 is over here. Then let us say this is line number 3, 4, and 5. We had total 4. So total 5 of the full lines are there, and the one half plane was there. Like 5 full plane was there, and one half plane was there. Now that half plane has moved over here. It is over here. Now it is a part of the surface. Now it is not considered as a dislocation. Now it is a part of the surface. It is going to create a step at the surface. And the step will be of the Burgess vector. The magnitude of the step will be of the Burgess vector. So now here we can say that what is going to happen? A crystal remain unchanged? No. There is the changes has occurred within the crystal that the dislocation has annihilated. So this is incorrect. A surface step of the magnitude equal to the Burgess vector is formed. That is right. Option B is the right answer. We can say that the step has been created. This is a step. And the step is of the Burgess vector. And it is at the surface. The dislocation get annihilated. And this is right. So this location will get annihilated. That is the right answer. So from here we can say that it's get to the surface. It's no longer over there. The crystal undergo the phase transformation. No, it's not the case. So we can say that the option B and C are the correct answer. Let's move to the next question. Question number 70. Again, match the pair type. Dislocation motion. Sorry, glide motion. So glide motion, and here are the terms will be written over here. We know the glide motion we have observed in the case of screw and edge both. So it's a possible for edge, screw, and the mixed dislocation. That's the correct one. One is going to match with the A. Cross slip. Cross slip we know that it's only going to happen in the screw dislocation. So possible for the screw dislocation. Option B is the right answer. Climb. Climb take place in the edge dislocation. It doesn't occur in the screw dislocation. So possible only for the edge dislocation. So 3 is going to match with the E. The Burgess factor in the edge dislocation. Now they're talking about the edge dislocation and the dislocation line. Their reference is the dislocation line, not the stress. Burgess factor in the edge dislocation is perpendicular to the dislocation line. We are aware about this. Dislocation line, you can consider it with a tangent vector. While for the screw dislocation, it is a parallel. So it will be the C and D. So this is our final answer. Okay. So if there is any doubt, you can let me know. If not, then we'll move to the next question. Now it's a true and false type. Let's do it one by one. First one, all type of dislocation can glide. Is it true? Glide, we know that it has been observed in the screw, it has been observed in the edge dislocation. So for the mix also it is the case. So more or less, yeah, we can say that it's a true. Second one, the cross slip motion is observed in the edge dislocation. So cross slip they are talking about. Cross slip, we know that it's observed only in the screw dislocation. So it's incorrect, false. Third one, the critical resolve shear stress is the minimum stress required to move a dislocation. That is correct. Right. So we can write this is a true. It is the minimum amount of stress that a dislocation will need to start the motion. So they are talking about the toss CRS. Uh, Let me tell you, the concept of this CRS, critical resolve shear stress, is going to discuss in the more detail in the upcoming week. So we will be little patient about that. And now, fourth one, climb motion can occur in both edge and screw. They are talking about the climb, not the glide. And we know that the climb is take place only in the edge dislocation, not in the screw. So this one is a false. Fifth one, a screw dislocation. In screw dislocation, the direction of the applied stress and the dislocation motion are the same. So they are talking about the screw dislocation and they are talking about the applied stress, that is toss CRSS. And the dislocation motion they are talking about. Dislocation motion, we can say that, see, here we have studied that the dislocation motion, if we talk in the screw dislocations, dislocation motion is perpendicular to the dislocation line Burgess vector and the toss CRSS. So here it is telling that the direction of they are the same. So the toss CRSS and the dislocation motion, they are parallel to each other. That is, while we know that it's a perpendicular. So again, it's incorrect. So we will write false. And with that, we have solved this question number 18. Let's move to the next question, question number 19. Just a minute, guys. Yeah. Now, the new concept of homophase and heterophase we have discussed. In a homophase interface, what remains the same across the interface? Homophase means that the means same. Phase means uh, the phase like alpha, beta, those things which we talk about, right? So now the orientation, no, it's not about the orientation. Crystal phases, that is the correct one. The homophase, the phases will be different. Sorry, phases will be same. The chemical composition will not bother about it. We are majorly concerned about the phase and not density and all no. So these all are incorrect. The option B is the right answer. Let's go to the option number. Question number 20. Which of the following is a type of homophases? like about which the phase is not going to change. Grain boundary, okay, yeah, we know across the grain boundary, before and after the grain boundary, the phase is going to remain same. Twin boundary is again the defect, but it's not going to change the phase. Solid and gas interface. Now, if we talk about the interface where below is a solid and above is the gas. So now this is a heterophase. The phase is changing from solid to liquid, so it's the incorrect answer. D is a stacking fault. Stacking fault is again the homophase planar defect. With that, you have solved this question number 19 and 20. Okay, let's solve the question number 22. Here we can say that the stacking fault is there, and we have to match with the correspondingly the column B. The stacking fault is the one which is, we can say that the translation boundary AB AB stacking, ABC ABC stacking, stacking fault displacement, rotation boundary. Stacking fault is the one which we have got by the translation boundary. It's a translation boundary only. If we translate that boundary by a particular amount, the fault will disappear. And if we translate the particular that is by that particular amount, by that particular that is translation, we will get that okay, a stacking fault has been created. Now, so first one is going to match with the A. Cubic close pack we talk about, CCP, that is presented cubic. It will going to form the ABC stacking. That is the option C is the right answer for it. Hexagonal close pack, if we talk about it, will form the AB stacking. That is option B is the right answer. Now for the grain boundary. Grain boundary, we know it is a rotation boundary. We rotate by the, like their orientation are different, right? Across the grain boundary. So if we rotate by one crystal with respect to the second crystal, then we can make them same orientation. So the grain boundary is the one which is bifurcating two grains, and they are the rotational boundary, we can say. Now lattice translation, non-lattice translation. Non-lattice translation are the one which are going to generate the stacking fault. So we will say that the stacking fault displacement. That is option D is the right answer. With that, we have solved this question number 22. Let's move ahead. Let's go to the question number 23. We are left with only two questions till now, right now. So now, regarding the true and false, a stacking fault change the overall orientation of the crystal. Does it change the orientation of the crystal? No. We can say that the grain bond is the one which has changed the orientation of the crystal, not the stacking fault. So it's a false. In a stacking fault, a single plane is displaced, causing a sequence disruption. That is true. Only one particular plane we can add, or one particular plane we can remove, and that will something which is going to lead to the formation of the stacking fault, and which is going to the abrupt what we can say that the sequence it will be disrupted. Like for example, it should be ABC, ABC, ABC. Then it will form ABC, but in between AB and AB again will be there. So the sequence will be disturbed. So this is the true. A stacking fault in the CCP structure result in local SCP arrangement. Yes. So let us say our CCP should be like ABC, ABC, and ABC type. Let us say now we are removing this particular C from this particular and sequence. This C has been removed. What we'll get? We'll get AB, C, AB, AB, and then C and ABC. It will continue so on and so. Locally, we can say that there is a sequence of AB, AB. So in the CCP, we are getting the AB, AB pattern. It means that we are getting the SCP type of pattern, SCP type of sequence. So it's a true. The stacking fault can be considered as a point defect. No, we know that it's a planar defect. It's not a point defect. So, 4 is incorrect. So it's a false again. Let's move to our final question, question number 24. Now, which of the following statement would be effective in the moving a screw dislocation that is lying along the z direction? So again, the point which we should remember that we are talking about the screw dislocation. In screw dislocation, we know that if you want to move a dislocation, if you want to move the, like let's say the screw dislocation lying along the z direction, that is the its t cap is along the z direction. It's along the, we can say that the along the k cap. If I want to move this, if I want to move this, it's lying along the z direction. We know if I want to move this, I have to apply the force, apply the shear stress along the same direction itself. Because here we have considered that in the screw dislocation, the dislocation line and the stress applied should be parallel with each other. So if the stress, if the dislocation is lying along the k cap, that is along the z direction, so my critical resolve shear stress, tau CRSS, should also be along the k cap. It should also be along the z direction. So a shear stress on the xy plane in the x direction? No, not in the x direction. XY plane in the y direction? No. It's along the YZ plane. So that means okay, YZ plane is there. In this plane we are talking about applying this particular plane and along the Z direction. So we got our direction. Since we got our direction, that's along the Z direction, so it is going to move. It's like both are parallel with each other right now. Tensile stress is not going to be the not it's not the one which causes shear to occur. So with that, we have solved a few questions in this particular class. I hope these questions will be very useful to you in solving the doubt, in solving those assignment questions. You will find this question number 24, to be similar with the assignment question number 1. So if you have understood this, you'll be able to solve that question also. So let's move one by one from what in all. These are the list of the topic that has been covered. Then we discuss about the few questions like mostly about dislocations, like how they are terminating, node, what are the stacking fault, void has been created. Then we talk about the screw dislocation, edge dislocations. We talk about the single crystal and the polycrystals. This type of questions which has been done. Then we talk about that some topics about the grading boundaries. We talk about what is the Burgess vector, and how it is related with the dislocations. We talk about the Frank rule, Burgess vector, tangent vector, and the dislocation node in detail. Then we discuss about that how the dislocation loop has been formed, like on what and the possible way a dislocation can end. And then we talk about the prismatic loop. Then few questions like on the similar type of stuff, like S screw and the mixed dislocation. Again, we talk about how the Burgess vector of the edge dislocation and the screw dislocation differ from each other. And then we talk about the motion of the screw dislocation under the shear stress. Under what condition, like if the dislocation is of the edge nature in the and the dislocation is of the screw nature, how differently they are going to behave? Like in what direction we should apply the stress, or in what direction the Burgess vector will lie. So those thing has been discussed. Then we talk about the surface, like if the dislocation get onto the surface, what is going to happen to the crystal? These are the list of the things that has been we did, and the true and false type of questions we tried for that. The okay, which dislocation can climb, which one can glide, which can do the both. Those things that has been discussed. We talk about the homophase and heterophase, and then after that we talk about that SCP, the stacking fault, that the sequence of the SCP and the FCC crystals, and And at the end, we talk about like this a questions which is similar to the assignment question. So that was all from my side. If you feel any doubt in this particular thing, in this particular in this particular lecture, please feel free to text onto the YouTube channel, or you can also comment on the what we can say that the dot solving forum where we discuss a lot of stuff. We will definitely respond to those questions and will clear all your doubts, whatever you are having. So we can end this particular session now. Bye bye. Let's meet in the next upcoming week 7 content. Once it get over, we'll again meet on the 8th of March. Okay. Okay, guys. Bye bye.